Hi there, this is Jeremy Krug, and if you're watching this video, then you are in the final days before the AP Chemistry exam, maybe even the final hours before walking into that exam room. It's time to cram. This is a long video, but I think you'll find it's worth it. Don't forget to print out the free guided notes PDF linked in the description down below. That will help you follow along with me as I review and work the problems in this video. And if you want a more comprehensive review, then head over to ultimatereviewpacket.com, where you'll get much more than just a cram session. You'll get every review resource you could ever need to score that 5. Study guides, unit summary videos, 2 full practice exams with answer explanations and walkthroughs for every single question. So head over to ultimatereviewpacket.com and click on AP Chemistry to get access today. Now, if you've printed off your free PDF of notes for this video, you're ready to sit back, get your calculator ready, relax. Well, don't get too relaxed because we're about to cram. Let's get started. Now, generally speaking, I'm going to be working through the entire course, units 1 through 9, and so we're starting kind of at the beginning here at unit 1. And so mass percent is an important concept to be able to grasp. For example, if we have this chemical compound, magnesium chloride, and you want to find out what percentage of that compound is magnesium and what percentage of that compound is chlorine by mass, it's really a very simple process. You take the atomic mass of each of the elements, so in this case magnesium is about 24.31, and then we have chlorine, which is about 35.45, but notice we have 2 atoms of that in the compound, so we have to times that by 2, which gives us about 70.90. Now, we add these values together, so the total molar mass of this compound is 95.21 atomic mass units. And then we take the individual total value for each element and divide it by the total molar mass. So in the case of magnesium, we'd take this 24.31 right here, and we divide that by the total, which is 95.21. So when you divide that out, and of course times it by 100, you find that the mass percent of magnesium is about 25.53%. And we can do the same thing for chlorine. We just take the 70.90 and divide that by the total, 95.21, and times that by 100, and you find that its percentage is about 74.47%. That's all you have to do to find the mass percent, and that works for any compound. Now let's try a different one. Let's try calcium chloride this time. Now once again, calcium has an atomic mass of 40.08 atomic mass units. Chlorine is still 35.45, and we have 2 of those atoms, of course, so that's still 70.90. And once you add those together, we get that the total molar mass here is 110.98 atomic mass units, AMU. And so to find the mass percent of calcium, we just take the 40.08 divided by the total, and we get 36.11%. And then the same thing for chlorine. We take the 70.90 and divide that by the total, which is 110.98. We find that that's 63.89%. So that's how you'd find the mass percent of any element in a compound. Now, of course, if we do everything right, the percentages should add up to 100, and it looks like they do here. Now, one little detail that you might have noticed, notice that we have 2 different chlorides here. And there's a little pattern that you might notice, that everything else being equal, the lighter the other element in the chloride, the greater the percentage of chloride in that compound is. So magnesium was a fairly light metal at 24.31, and so it made up less of a percentage in the total. Calcium is a little bit heavier, 40.08, so it makes up a somewhat larger percent in the chloride, and then the chloride would be less there. Now, what if we had beryllium chloride? How would that compare? Well, you might realize that beryllium is a lighter metal than magnesium or calcium. In that case, the beryllium would have a mass percent of somewhere less than 25%. and the chloride would be higher than 74 or 75%. What about strontium chloride though? Well, strontium is heavier than magnesium or calcium as far as its atomic mass goes. So that means that the strontium would make up a greater percentage than this 36%, and the chlorine would be less than 63% in strontium chloride. So think about those patterns, because sometimes they like to ask multiple choice questions about mass percent, comparing the amount of chloride or some other element in different compounds. Now let's move on and take a look at mass spectrometry. Sometimes this is called mass spectra of elements. For any pure element, we can basically get a graph from a mass spectrometer that looks essentially like this. Now, whenever you have two bars here, this tells us that that element has two isotopes. And so in this case, we have the two isotopes, and one of the isotopes has a mass of about 85 atomic mass units, and the other one has an atomic mass of about 87 atomic mass units. Now, each of the heights of those bars represents the percentage abundance. And so in the case of the one that has a mass of 85, its abundance is about 75%, or at least that's what it looks like on this bar graph here. And then the one that has a mass of 87 is about 25%. So if we take those individual atomic masses and multiply them by the decimal equivalents of their percentage abundances, we get these numbers here. If we add those together, that should give us the average atomic mass of the element. So in this case, we have an element that has an average atomic mass of around 85.50 atomic mass units. All we have to do is compare that to the periodic table, and we can see that this is most likely the element rubidium, because it has an atomic mass very, very close to that. So this is the idea that you want to have whenever you're presented with a graph or a mass spectrum that looks something like this. Now let's take a look at electron configurations. It's important to be able to write electron configurations. Now, of course, they're not going to give you this graphic on the exam, but if you're familiar with that, you're going to be able to write an electron configuration for any element that they could throw at you on this exam. For example, if we're trying to write the configuration for the chlorine atom, remember, we always start at the beginning of the table and we work our way through every sublevel, through every section until we get to our goal. So in the case of chlorine, which is right here, its electron configuration is 1s2, then we have 2s2, then 2p6, we have 3s2, and finally 3p5, because it's 1, 2, 3, 4, 5 boxes into that sublevel. Now, what if we change the question? What if we ask instead for the electron configuration for the chloride ion, Cl negative? In that case, we want to realize that an anion has gained electrons. And in this case, since it's Cl negative, it's gained exactly 1 electron. And that electron is going to be added into that valence shell, that last shell. So we're going to change the 3p5 to 3p6. And so that's how you'd write the electron configuration for the chloride ion. Now, how about the aluminum atom? Well, the same idea here. We start with 1s2, then 2s2, 2p6, 3s2, and finally 3p1. And so that's the electron configuration for aluminum. Now, what about the aluminum 3 plus ion? Well, since it has a positive charge, it's going to lose 3 electrons, and it's going to lose those 3 electrons out of the valence shell. So that's the outermost shell represented by the largest coefficient there. So that means that these 3 electrons right here, 3s2 and 3p1, are basically going to go away. And so here we have the electron configuration for the aluminum cation. It ends with 2s2, 2p6. Now let's try another one. How about the fluorine atom? Well, fluorine is right here, and its electron configuration is 1s2, 2s2, 2p5 in this case. So that's the electron configuration for fluorine. Now, what if we do this? What if we have the F positive ion? Now, if you have worked your way through AP Chemistry, you probably will look at that charge and say that that looks kind of funny. Fluorine normally has a -1 charge, but what if it did have a positive charge? Well, it would remove one electron, and it would remove one electron from that last sublevel, which is 2p. So it would actually be 2p4 in this case. So that's the electron configuration for F positive. Now, how about germanium? What about this somewhat longer configuration? Well, we start from the top. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and it's 4p2. So that's the electron configuration for germanium. Using this method, you can write the electron configuration for pretty much any element that they could throw at you on this exam. Now, speaking of electrons and electron configurations, let's take a look at a periodic table trend. And probably one of the most important ones is atomic radius. It's important to realize that the largest atoms as far as radius will be at the left and the bottom of the table. So that would be these atoms kind of down here, closer to cesium and francium and barium and radium, kind of in that corner of the periodic table. That's where you're going to have the largest atoms. Now, the reason for this is that atoms at the bottom of the table have more electron shells. And as a result, that last electron shell tends to be farther away from the nucleus. And so that's why your atoms at the bottom of the periodic table have a greater radius. Now, how about on the left? Well, on the left side, we want to talk about it in terms of protons and effective nuclear charge. Atoms on the left side of the periodic table have fewer protons than atoms on the right side of the table. And so because of that, that smaller or that less effective nuclear charge means that those atoms on the left side are going to have fewer protons to pull in those electron shells or those energy levels. And so that's why atoms on the left side tend to be larger, atoms on the right side tend to be smaller. Now, one mistake that students often make on the AP exam is they will try to explain why something is larger or smaller in terms of where something is on the periodic table. Don't make that mistake. Don't say that, for example, cesium is larger than lithium because cesium is farther down on the periodic table. That's not an explanation. That's not a reason. The reason is, cesium has more electron shells, and so its last shell is farther away from the nucleus. So be very careful as to how you make those explanations. Never use location on the periodic table as an explanation for anything. That doesn't explain, that just is a trend. Now, another important trend is ionic radius. And so here we have a general trend that, as you can see here, positive ions, these cations, which I have in blue, tend to be smaller than anions, or those negative ions, which we have in pink. And if you look at this, it kind of makes sense as you think about why that is. Let's just take 6 ions that all have the same number of electrons. And so the nitride ion, which is right here, and the oxide ion and the fluoride ion, as well as sodium, magnesium, and aluminum ions, all have the same number of electrons. And so if you were to write the electron configuration for all 6 of those, you'd find that they all have the same electron configuration. They're what's called isoelectronic. And so what that means is, because of that, the atom that has more protons is going to be able to pull in those electrons more effectively. And so the one that has the most protons here is aluminum. And so aluminum is going to be able to pull in those 10 electrons much more tightly. And that's why the aluminum cation has a radius of a very, very small amount, something like 57, I think is what that says, 57 picometers, whereas nitride has a lot fewer protons. And so that's why nitride is something like 3 times as large as the aluminum ion. So once again, generally speaking, the more negative an anion is, the larger it is, and the more positive a cation is, the smaller it's going to be, and that's ionic radius. Now, another important trend is first ionization energy. Now, generally speaking, first ionization energy, which by the way is how much energy it takes to remove that very last electron from an atom, it tends to be the greatest toward the right and the top of the table. So that would be these atoms over here, things like helium and neon and fluorine. Those are going to have the highest first ionization energy. And basically the reason is the same as it was before. At the top of the periodic table, we have fewer electron shells. And that means that that last shell is closer into the nucleus, and it has stronger attractions to the outermost electrons. And so it's going to require more energy to pull that last electron, since that last electron is closer to the nucleus and has that stronger attraction. On the other hand, the ones at the bottom of the table, you have more electron shells. And so that last electron is just farther away from the nucleus, and so it's not held in as tightly. The Coulombic attractions are weaker, and so it requires less energy to pull that last electron. Now, if we're talking about left and right, we want to think about this in terms of the number of protons and the effective nuclear charge. The ones that are farther toward the right have more protons and greater effective nuclear charge. And so the protons are pulling in those electron shells more tightly, and so it's going to require more energy to remove that last electron from, say, neon over here than it would from lithium over here. So, more protons means a stronger Coulombic attraction, a stronger effective nuclear charge. Now, let's take a look at one more concept here in Unit 1, and that is photoelectron spectroscopy. So they like to ask these questions. I can pretty much guarantee that you'll see at least a graph or two like this on the exam. And the way that you read a photoelectron spectroscopy diagram is you just read from left to right. Each peak represents a sublevel. So this first one is 1s, for example, and then it's 2s, and then 2p, and then 3s, and then 3p. So if you can write an electron configuration, you can read a photoelectron spectroscopy diagram. The height of the peak has everything to do with how many electrons are in that sublevel. So we have 3 peaks that are these S peaks here that all have the same height. So it's safe to assume that they all have 2 electrons in them. So I just have 2 there. Now, this 2p peak is 3 times higher than the S peak. So that tells me that this is 2p6. And this 3p peak is more than twice as high, but not quite 3 times as high as the S peak. So that tells me that it has 5 electrons. So it ends with 3p5. So if I think about the electron configuration for this, this tells me that this is the electron configuration, or the PES diagram for chlorine. Now, we can do something different here. Let's take a look at another PES diagram. Do the same thing. We have 1s, 2s, 2p, 3s, and 3p. And then we have 2, 2, the next one is 6, and then we have 2, and then that last one is 6 as well. So this element seems to be argon. Now, one little detail that sometimes they will ask about on the AP exam is the left and right. I want you to notice not just the height or where the peaks are, but notice where they are on the x-axis, the relative binding energy per electron. Generally speaking, the more protons an atom has, the greater the binding energy of its core electrons. And so if you look at argon here, notice that the 1s and the 2s and those 2p electrons are just a little bit scooted over to the left on this diagram. That tells me that that has more protons, and it's pulling in those electrons more tightly. It has more binding energy. And so anytime you see a peak farther to the left, it probably has more protons. And so even if I did not have the numbers and the letters and all the labels on here, I would be able to tell that the second diagram here has more protons than the first diagram. So that's a little detail that they like to ask about on the AP exam as well. So just be aware of that. Let's jump right into Unit 2 here, and we're going to take a look at Lewis electron dot diagrams. That's kind of the heart of Unit 2 here. And we're going to start with sulfur difluoride. So once again, you always put the central atom in the center, so sulfur's in the middle. Personally, I like to start with the outside and work my way in. I find it reduces mistakes. And so every fluorine atom has 7 valence electrons, so I'll put 7 dots around that fluorine and 7 dots around that fluorine. And then the sulfur is going to have 6, and so we have 6 dots there. And everything is trying to have 8 for the most part. So everything has 8. And so I'm going to replace these shared pairs with a little line here. And so here's how I would draw the finished Lewis electron dot diagram for SF2. Looks like this. Now, how about COCl2? Well, once again, I draw the central atom in the middle, and normally they will tell you or make it fairly obvious what the central atom is. In this case, it is carbon. So that goes in the middle. We have 7 valence electrons for every chlorine, so we have that. We have the 6 valence electrons for oxygen up there. Carbon brings in 4 valence electrons. And once again, the goal is for everything to have 8. And the way I have this drawn, everything does not have 8. And so I need to bring maybe 2 valence electrons from the top of this oxygen down to the middle here, just like this. And now everything has 8. So this time I have a total of 4 shared pairs. There's a double bond here between the carbon and the oxygen, and we have 2 single bonds, one between each of the chlorines and the central carbon atom. So that is our finished Lewis electron dot diagram for COCl2. Now, if we take a look at some Lewis electron dot diagrams, it is important for you to be able to understand the types of bonds that it has. Sigma and pi bonds, for example. Every single bond is a sigma bond. Every double bond has 1 sigma and 1 pi. Every triple bond has 1 sigma and 2 pi. So in this molecule here, since we have 2 single bonds, we have 2 sigma bonds. And then the hybridization is sp3. We have to think about that because there are 4 electron regions or 4 electron domains around the central atom. It has a steric number of 4. These are all different ways of saying the same thing. There are 4 of these electron regions or electron domains around the sulfur, which corresponds to a hybridization of sp3. Now, in this one here, we only have 3 electron regions or electron domains around that central carbon atom right there. So because it has 3 electron domains, it has a hybridization of sp2. Now, how many sigma and pi bonds does it have? Well, we have 2 singles and 1 double bond. So every double bond has 1 sigma and 1 pi. So that's why it's 3 sigma and 1 pi bond. The hybridization is sp2, like we said. Sometimes you'll have molecules that have multiple central atoms. In this molecule here, we actually have 3 central atoms. Each carbon is a central atom, and then the oxygen acts as a central atom as well. So when you add up the types of bonds here, we have, looks like 1, 2, 3, 4, 5, 6, 7 sigma bonds, and I see 1 pi bond because there is a double bond over there. And the hybridization, each central atom has its own hybridization. So carbon number 1 has 4 electron regions or electron domains. So that's sp3. Carbon number 2 has 3 electron domains. So that's sp2. And then the oxygen atom has 4 electron domains. 1, 2, 3, 4. So that would be sp3. There's no shortcut around that. You have to know the hybridizations and be able to give the hybridization of every central atom in a molecule when there are multiple central atoms. Now, let's take a look at another detail here, and this is the concept of molecular geometry and bond angles. So we'll go back to that first molecule that we looked at earlier, and notice that since it has 2 bonding regions here, or it's bonded to 2 atoms, and it has 2 lone pairs, 2 and 2 is bent. And it has a bond angle of about 104.5 degrees. Now, if you look at the structure the way we have it drawn here, you might think its bond angle is 180 degrees. Well, it's not. It's a bent structure, and that's why most chemists will draw it more like this, actually. Now, the second structure, it looks like we have a total of 3 bonding regions, 1, 2, 3. It's bonded to 3 atoms. 0 lone pairs, so 3 and 0 is trigonal planar, and that bond angle is 120 degrees. Now, on the next one, we have 3 central atoms, so there are actually 3 molecular geometries. You have to be able to describe all of those. The first one is 4 bonding regions and 0 lone pairs, so that's tetrahedral. And then the next one is trigonal planar again. We have bonded 3 atoms, no lone pairs, so that's trigonal planar. The oxygen is bent because it has a bond to 2 different atoms and 2 lone pairs. So that's 2 and 2, so it's bent. So we actually have 3 molecular geometries in the same molecule here. You have to be able to do that. It will have 3 different bond angles as well. Tetrahedral is 109.5 degrees, trigonal planar is 120 degrees, and bent is 104.5 degrees. Now, if you have a little trouble getting all these bond angles straight, on the AP exam, they're a bit more lenient than your teacher might be, because anything that has a hybridization of sp3 and has 4 electron domains, they're okay with it if you just call it 109.5 degrees. And so if you say bent is about 109.5 degrees, that's fine. They're not going to count off because of that. Now, let's take a look at one other concept. This is the concept of polarity. Sometimes they'll ask the question, does this molecule have a dipole moment? And what that means is it a polar molecule or a nonpolar molecule? Well, anytime you have a bent structure like this, it is a polar molecule. It does have a dipole moment. And one thing that you need to remember here is that it's not about symmetry. Okay, I noticed that some students want to talk about this in terms of symmetry, and that has nothing to do with this. It's not symmetry, folks. It has everything to do with, is there an unbalanced region of negative charge in the molecule? And so all 3 of these molecules, you could make a case they're all symmetrical, but that doesn't mean they're all nonpolar. In fact, obviously this is polar because we have an unbalanced region of negative charge. We have these 2 lone pairs of electrons hanging out on that sulfur atom right there. So that is a polar molecule. Every molecule has London dispersion forces. So you need to know that. Now, if it's a polar molecule, it also has dipole-dipole forces. So that first molecule has both of those. Now, the next one, this is also a polar molecule. And that's because there is this unbalanced region of negative charge on that oxygen. Now, this may not be quite as polar as the first one was, but it is a polar molecule because it has a lopsidedness in its electron distribution. And because of that, it also has London dispersion forces and dipole-dipole forces. In the third one, there is no unbalanced region of negative charge at all. In fact, there are no lone pairs to speak of at all on this molecule. So this is a nonpolar molecule. And because of that, it has only London dispersion forces. Now, we need to realize there's this thing called hydrogen bonding as well. If you have a molecule that has a hydrogen bonded to an FO or N atom, it's going to have hydrogen bonding. Hydrogen bonding can be classified as a kind of a type of dipole-dipole force. If you have a molecule like water, you want to say it has London dispersion forces and hydrogen bonding. You don't have to say that it also has dipole-dipole forces. That's kind of understood if you say that. Some people would say that hydrogen bonding is completely different from dipole-dipole. I guess the jury is still out on that. But if you say something has hydrogen bonding and London dispersion forces, you don't have to say that it also has dipole-dipole. That's just a little clarification on that one. Now let's take a look at a different concept here from Unit 2, and that's the concept of melting points here. And this goes right back to Coulomb's law, which is kind of a thread that we see quite a bit, especially in the first half of this course. So let's say that we're trying to compare the melting points of sodium chloride and sodium sulfide. Well, you want to think about this first of all in terms of charge. Sodium and chloride, that's a +1 -1 pair, and sodium sulfide is a +1 -2 pair. So we would expect the ones that have the greater magnitude of charge to have the higher melting point. And sure enough, that's exactly what happens. Sodium sulfide has a higher melting point than sodium chloride. Now, what if we have two ionic compounds that have the same ion charge in them? So like aluminum chloride and aluminum fluoride. If they're the same, the tiebreaker is to look at the sizes of the ions. Because we know that chloride is a larger ion than fluoride, that means that the chloride ion is going to be larger and the ion centers will be farther from each other than they are in aluminum and fluoride. So in aluminum and fluoride, since the ions are closer to each other, the attraction is higher. And so it's going to require more energy to melt that. And so you'd expect that the smaller the ions, the higher the melting point. And if you look at the melting points, that's exactly what you have. Aluminum chloride melts at about 192 degrees. Aluminum fluoride melts at about 1,291 degrees. That's a lot higher because the ion sizes are much smaller. Now let's compare the melting points of sodium chloride and potassium bromide. Well, once again, the first thing we do is look at the charges. +1 -1, +1 -1. Well, since it's a tie, then we look at the ion sizes. So we see that sodium and chloride ions are smaller than potassium and bromide ions. And so that tells us that sodium chloride should have a higher melting point and potassium bromide should have a lower melting point. And sure enough, that is exactly what you have. Sodium chloride is, several degrees higher in its melting point. And that's because sodium and chloride are smaller ions, so their Coulombic attractions are going to be stronger. Now, as we think about how ionic compounds are arranged, there's this three-dimensional lattice. Now, I don't have it drawn in 3 dimensions here, but you kind of get the idea that every ion is surrounded by ions of the other type of charge. We have positives and negatives attracting each other. So here we have sodium fluoride. Now, when this dissolves in water, we need to realize that the water molecule is a very polar molecule. So we have the negative pole of water, which is the oxygen, and we have the positive pole of water, which is the side that the hydrogen is on. Well, the positive poles of water will surround these negative ions and literally drag them off into solution. And the other side of water, the negative pole, is going to surround those positive cations and literally drag those off into solution. So imagine all these water molecules doing that to these other ions. And as long as those ion dipole forces between the water molecules and the ions are stronger than the ionic forces holding the crystal together, it's going to be soluble in water. And sodium fluoride is soluble in water. Now let's take a look at Unit 3 here. We'll jump right into a gas law question. And we have a problem. We have a gas mixture that's collected in a 3-liter rigid container at a temperature of 315 kelvins. It says that the pressure inside the container is measured to be 1.14 atmospheres. How many moles of gas are in the mixture? So on a problem like this, you want to use the equation PV equals nRT. We're basically just going to plug and chug right into that equation. P, the pressure, is 1.14 atmospheres. V, the volume, is 3.00 liters. We're trying to solve for N, the number of moles. R is the universal gas constant of 0.08206 liter atmospheres per mole Kelvin. And the temperature is 315 kelvins. So all we have to do is use algebra to solve for N, and you find that the number of moles is 0.132 moles in this mixture. Now, what if we go a step further? What if it is determined that 0.045 moles of the mixture is oxygen? the other gas would compose how many moles? Well, when you have a gas mixture, we know that the two individual mole values are going to have to add up to the total number of moles in the container. So in this case, if the total number of moles is 0.132, and we subtract out the 0.045 moles of oxygen, we find that the other gas is 0.087 moles. Now, what if we go even a step further? What if we determine that that other gas that we just found the number of moles of has a mass of 3.47 grams? What's the molar mass of that gas? Well, remember, molar mass is in units of grams per mole. So grams per mole implies grams divided by moles. So we just have to take the number of grams, which is 3.47 grams, and divided by the number of moles, which we just said was 0.087 moles. And when you divide that out on your calculator, you find that the answer is very close to 40 grams per mole. And so you could take a guess as to what that gas was. It sounds like there's a good chance it's argon. So it might be that, or possibly some other gas that has a molar mass of 40 grams per mole. Now let's take a look at spectrophotometry, because they're going to ask you something about this. The Beer-Lambert law is used to talk about spectrophotometry very often. Whenever you have a spectrophotometry problem, you're very likely going to have a graph like this. And we always run a blank, and then we run several known concentrations and we record those absorbances. So we just plot those there on the XY axis, and then we draw a best fit line. So a line that kind of best connects those, or best approximates those points there. And then we determine the absorbance of the unknown and match it up to the concentration. So for example, if we have an absorbance of 0.2, all you'd have to do is match that up to the line like this, and you'd find that its concentration is very close to 0.55 moles per liter. And so that's how you match something up to a calibration curve using spectrophotometry here. That is literally how that's done in the lab. Now, one thing you want to be careful about is outliers. Occasionally they'll ask you a question about outliers. If we have a dot like this one right here that's a little bit too high, that most likely means that the sample got contaminated with a concentration that was too high. If you have something like this, a dot that's too low on the XY axis here, that tells us that the sample was probably contaminated with something that had a concentration too low, or more likely with distilled water or something that had basically a contaminant in there. So just be aware of that. I have a much more detailed description of that in my daily videos there for Unit 3, Topic 13, if you want to see something in more detail about that. Now, an important thing we have to be able to do in Unit 4 is understand net ionic equations. So for example, if you have this sentence here, a piece of magnesium metal is added to a solution of copper 2 chloride. We need to remember that there are three things that are basically in that solution. We have magnesium metal that's been added, and we have two ions in solution. We have copper 2 ions, and we have chloride ions. And we need to understand that metals generally react with metal ions, and nonmetals generally react with nonmetal ions. And so here we have a metal, which is magnesium, reacting with a metal ion, which is copper 2+. So what's the chloride doing there? Well, the answer is it's not doing anything. Chloride is the spectator ion. It's just sitting there looking on like a spectator, basically. So it's not going to be included in the net ionic equation. One of the most common mistakes that students make when writing net ionic equations is they try to put those spectator ions in there somewhere, or they completely forget to omit those. And so make sure that you leave out spectator ions in net ionic equations. So Mg is going to react with Cu2+. Now, generally speaking, metals get oxidized. That means the charge goes up. So magnesium is +2. And then metal ions normally get reduce down into their metallic form, so down to Cu. Now we have to balance these half reactions in terms of charge. We see that we have a 0 for magnesium, Mg2 plus of course is 2 plus, so to balance that in terms of charge, we have to add 2 electrons over here, and then kind of the same thing for copper, we have to add 2 electrons on the left side over here to make that work. And so now we can add these two half reactions together, the 2 electrons cancel out, and we have our overall net ionic equation here for a redox process. It's important to understand that since in this first half reaction we're losing electrons, that's called oxidation. And in the second half reaction, since we're gaining electrons, that is reduction. So be aware of the difference between oxidation and reduction. Some people like to say, Leo the lion goes grr. Lose electrons is oxidation, gain electrons is reduction. As we move on, we can take a look at some other basic ideas here. Sodium metal is burned in air. Well, we know that that's Na. And anytime you burn something, you're adding oxygen to it. So the product is going to be something made of NaNO, which is Na2O when you look at the charges. If you're ever asked to write an equation, you want to balance the equation. So we can balance the equation by adding a 2 here to balance the oxygens, and then a 4 over here to balance the sodiums. If we have a sample of propane gas, C3H8, that's burned in air, well, we just write that out, C3H8, add it to O2, and the products of every complete combustion are carbon dioxide and water. And then you want to balance that equation. We have 3 carbons here. It looks like we need to balance the hydrogens by putting a 4 right here. And then for our oxygens, we have 6 plus 4, so that's 10 oxygens versus 2 right here. So a 5 right there will now balance that equation. Let's take a look at one more here. This is a good example of a precipitation reaction. Solutions of lead-3 nitrate and sodium carbonate are mixed in a test tube. So once again, we have solutions, lead-2 nitrate, we write them in their ion form. Sodium carbonate, we write sodium and carbonate in its ion form. And we have to realize that when these ions try to swap partners, only one combination is going to make a precipitate. The sodium and the nitrate are spectator ions. Anytime you see something with a sodium or a potassium or a nitrate, that combination will be the spectator ions. The other compound is actually going to make your precipitate. So in this case, it's Pb2 plus reacting with CO3 2 negative, and that's going to make lead-2 carbonate, which is PbCO3. So there is your product, and here is your net ionic equation. I like to put the state symbols in here. Ions are always aqueous. The precipitate, of course, is always a solid. Normally, you do not have to put the state symbols in there. They're optional unless they specifically ask you to write them in there. Now let's move on to a stoichiometry problem. In chemical reactions, it's very common that we're asked to work a stoichiometry problem. And one thing that I always tell my students is the first step is convert to moles. The second step is use the mole ratio. Usually those numbers come straight out of the coefficients for the balanced equation. And the third step is to convert to some other final unit, usually grams, if you're asked to do that. So let's do that here. We have a balanced equation, and it says in a chemical analysis, excess silver ions are added to a solution containing carbonate ions. After the reaction, the total amount of silver carbonate solid is weighed and found to have a mass of 0.347 grams. How many grams of carbonate ions were present in the original sample? So once again, I'm going to start by writing down what's given to me. It says that we have a mass of 0.347 grams of silver carbonate. And the question is asking how many grams of carbonate ions were present in that original sample. So way down here at the end, we're trying to convert to grams of carbonate. So like in any stoichiometry problem that we do, step 1 is convert to moles. So that means I have to put grams on the bottom and 1 mole on top. And we consult the periodic table and see that there are 275.75 grams in 1 mole of Ag2CO3. Now, grams are out, top and bottom. We're now in moles of silver carbonate. Step 2 is the mole ratio. So I take Ag2CO3 and put that on the bottom, since that's what we're trying to get rid of, and we're converting to carbonate. So carbonate goes on the top, and I can look in the balanced equation here and see that this is a 1-to-1 ratio. There's one carbonate consumed for every one silver carbonate produced, so 1-to-1. So I can cancel silver carbonate top and bottom. I'm now in moles of carbonate. I want to be in grams of carbonate. So step 3 is to convert to that final unit, which is grams. So moles go on the bottom, grams go on the top, and consulting the periodic table, it looks like there are about 60.01 grams in 1 mole of the carbonate ion. So I can cancel moles top and bottom, and when I do my math, the 0.347 divided by 275.75 times 60.01, I find that my answer is about 0.0755 grams of carbonate. So that's a very typical stoichiometry problem that we have there. Now let's take this a step further. Let's say that we have a student that adds 150 milliliters of 0.120 molar silver nitrate to a solution of excess sodium carbonate. Assuming the reaction goes to completion, how many moles of silver carbonate should be produced? Well, let's think about this first in terms of the moles of silver ion that we added to the solution. It says 150 milliliters of 0.120 molar silver nitrate solution. Well, the question is how many moles of silver ions were used? Now we can use the equation molarity equals moles divided by liters to figure that out. If you rearrange that, you find that the number of moles is just liters times molarity. So I take 0.150 liters times 0.120 molar silver ions, and I find that I had 0.0180 moles of silver ions added to the solution. So now I'm going to take that value and I'm going to determine how many moles of silver carbonate should be produced, because that's what the question is asking. How many moles of silver carbonate should be produced? So, in my 3-step process, I've just converted to moles. That's what I just did right there. So I can jump right into step 2, which is the mole ratio. So silver goes on the bottom, silver carbonate goes on the top, since that's what I'm converting to. And this time, it looks like it's a 1-to-2 ratio, because those are my coefficients for the balanced equation. So I can cancel silver, and this time I take 0.0180 divided by 2, and I find that the answer is about 9.00 times 10 to the negative 3rd moles of silver carbonate. So a couple of very straightforward stoichiometry problems. That last one there is a good example of solution stoichiometry. Now, as we jump into Unit 5, which is kinetics and rate laws, this is a very typical kinetics problem where you're given an equation and some sort of a table or a chart that looks like this, and you're asked to determine the orders of the reaction with respect to the different reactants. So in this case here, let's determine the order of the reaction with respect to the A2 molecule. So the key here is to find 2 trials where A2 is the only reactant that's changing concentration. And so I would recommend trials 1 and 2, because it looks like A2 is doubling from trial 1 to trial 2, whereas D2 is staying the same. So it looks like A2 is doubling, while the rate is basically doubling as well. So we have to ask ourselves, 2 raised to what power is equal to 2? Well, the power is 1. So that's why we would say that it is first order with respect to A2. Now let's do the same thing with the other reactant, D2. We have to find 2 trials where D2 is the only substance changing concentration. I would recommend trials 1 and 3, because it looks like A2 stays constant from trial 1 to 3, but D2 is doubling. So D2 is doubling from trial 1 to trial 3, but the rate seems to be going up by a factor of 4. So once again, we have to ask ourselves, what is the power here? If the concentration is doubling and the rate is quadrupling, What power is that? 2 to what power is 4? Well, it's the second power. And so that means that the reaction is second order with respect to D2. Now, the overall order of this process is just the sum of those two individual orders. So 1 plus 2, of course, is 3. And so this is overall a third order process. Now, let's take this a step further. If we're asked to write the rate law for this reaction, it's written in the format rate equals K times the first reactant, which is A2, raised to its order, which is 1, times the concentration of the next reactant, which is D2, raised to its order, which is 2. So the rate law is rate equals K times A2 times D2 squared. Now, the part of this that trips up students sometimes is determining the rate constant, because we're asked to determine the rate constant with proper units. And that's the tough part for some students. Let's just work through this. The way that you determine the rate constant is you just take the rate law and you plug and chug the values from any one of those 3 trials. Any one of those 3 trials should work. So I'm going to use trial 1 just because, well, it's the first trial. So in the first trial, the rate is 1.12 times 10 to the negative third molarity per second. Always conserve those units because the rate constant has to have proper units. Now K, the rate constant, is what we're trying to solve for. The A2 concentration in trial 1 is 0.040 molar, and the D2 concentration there is 0.030 molar, and that's got to be squared because it's raised to the second power. Now, once you plug this into your calculator, you take 1.12 times 10 to the negative third and divide it by 0.04 and divide it by 0.03 squared, you get about 31. Now, that's the numerical value, but you want to have the units on here too. Now, here's how you do this. You want to isolate the variable. We're trying to isolate that K right there. So I have a molarity times a molarity squared. So in order to isolate that, I have to multiply this side by molarity to the negative third to get rid of that molarity cubed. Now, if I'm going to do something on one side of the equation, I have to do it on the other side of the equation too. So on this left side, I'm going to also multiply by molarity to the negative third. And this molarity times molarity to the negative third is molarity to the negative 2. So the units are molarity to the negative 2 over seconds. We have that seconds we still have to put in there too. So that is our value for K with correct units. So be very careful as you're making that calculation. Now, there's another way to determine the rate law for a reaction. We can do this graphically. So if we have this reaction right here, 2HI yields H2 plus I2, you want to make 3 graphs. One graph is going to be concentration versus time. Another graph is going to be natural log of concentration versus time. And the third graph is 1 over concentration versus time. One and only one of those graphs is going to be a straight line. And I think we can all tell that it's this graph down here at the bottom. Well, if it's the 1 over concentration versus time, that is going to be second order. Now, if this graph up here, if concentration versus time had been a straight line, it would have been 0 order. And if natural log of concentration versus time had been the straight line, it would have been first order. But it was 1 over concentration versus time. That's second order. Now, the rate law, just like it's been done before, rate equals K times the concentration of HI squared. That squared, of course, comes from the fact that this is a second order process. And how would you determine the rate constant? It's equal to the slope of that straight line. If it's 0 order or first order, notice that those two plots are kind of going downhill, aren't they? So that means it would be negative slope if you were trying to find the rate constant of those. Just as a reminder, rate constant is always a positive value. Now, one last thing we have to realize for rate laws and kinetics is being able to work with reaction mechanisms. So let's say we have this reaction mechanism right here. Let's first of all identify the reaction intermediate. Now, once again, a reaction intermediate is a substance that is produced in an early step and then used up in a later step. So to me, it looks like it's BF2 because it's produced in step 1 and then it's consumed in step 2. It does not appear in the overall balanced equation. So BF2 is your reaction intermediate. Now, what's the overall balanced equation? Well, we just have to add these two equations together. It's kind of like adding two equations in algebra, basically. We have BF3 plus these two oxygen atoms yields B plus O2F2 plus O2F. And so there we have our overall balanced equation. Now, if we add a little bit of information in here and we say which of the steps is the rate determining step, we have to remember that the slow step is always the rate determining step. And so that would be step 1 because it is the slow step. And what's the rate law for the reaction? Well, essentially, the rate law of the slow step is going to be the rate law of the overall reaction. So it's just rate equals K times BF3 times O2, like this. Now, if the slow step happens to be the second step or a later step, then we have to use a process called pre-equilibrium approximation in order to find the rate law. I have a detailed video about that in my daily videos. But pretty good chunk of the time, it'll be the first step and you won't have to worry about that. Moving on to thermochemistry, we have a question here where we're going to use the equation Q equals MC delta T. Now this problem says a student adds 0.500 grams of warm copper metal to a 52.77 gram sample of water. After stirring, the temperature of the copper metal drops from 356 degrees Celsius down to 23 degrees Celsius. The specific heat capacity of copper metal is 0.385 joules per gram degree Celsius, and the specific heat capacity for water is 4.18 joules per gram degree Celsius. Assume that no heat is lost to the surroundings. So the first question here is, how many joules of heat were lost by the copper? So whenever we have a question like this involving specific heat capacity and joules and mass and temperature, we're going to use the equation Q equals MC delta T. Now the Q is representing joules, and that's what we're trying to solve for. So Q is going to be our unknown in this question. Now M represents the mass of the copper. It says this is 0.500 grams of copper. So that goes in there for M. Now C represents the specific heat capacity, and the problem says that that value for copper is 0.385 joules per gram degree Celsius. So that goes in for C. Now the change in temperature, it says it went from 356 degrees Celsius down to 23 degrees Celsius. So when you subtract that, you find that that's a drop of 333 degrees Celsius. So that's why I have negative 333 plugged in there for delta T. Now, once you multiply this across, you find that the value for Q is about negative 64.1 joules. Now that negative sign right there basically just implies that heat is being lost by the copper. That's what that negative sign means. Now, part B says, how many joules of heat are gained by the water? Well, the first law of thermodynamics tells us that we never destroy or create heat, it's just transferred in a chemical or physical process. And the problem tells us that we're assuming that no heat is lost to the surroundings. So if 64.1 joules of heat are lost by the copper metal, that means that 64.1 joules of heat must be gained by the water. Now, part C says, what was the original temperature of the water? Well, once again, we're going to use Q equals MC delta T, and this time the Q is 64.1 joules because that's the amount of heat gained by the water. Now, M is the mass of water, and it tells us that it is 52.77 grams of water, so that goes in there for M. Now, the value of the specific heat for water, the C, is 4.18 joules per gram degree Celsius, so that goes in for C, and we're solving for delta T. So now we just use algebra to solve for delta T, and you find that the value of that is about 0.29 degrees Celsius. So that tells us that the temperature went up by about 0.29 degrees Celsius, and we know that the final temperature of the copper and the final temperature of the water had to be the same. Whenever you drop something that has a very high temperature, like the hot copper in this case, into something much colder, like the cold water, the temperature of the copper drops and the temperature of the water rises until they both equilibrate. And so the final temperature of both the copper and the water are going to be the same. That's called thermal equilibrium. And it says that the final temperature of the copper is 23 degrees, so the final temperature of the water also has to be 23 degrees. So the initial temperature of the water had to be about 0.29 degrees less than the 23 degrees. So that tells us that the initial temperature of the water is somewhere around 22.7 degrees Celsius. So there's a very good and typical example of thermochemistry using Q equals mc delta T, working with calorimetry. Now, speaking of heat and how things change temperature and essentially just change as we add heat to them, let's imagine we have this heating curve. So here we start with a solid at a fairly low temperature, and as we add heat to that, notice that the temperature goes up. That makes sense. You add heat to a solid, the temperature is going to go up. And once it gets to the melting point, though, once it undergoes that phase change, the temperature is going to stay constant during that phase change. So while the object is melting, perhaps this is ice melting into liquid water, that temperature stays constant during the melting process. Now, once everything has melted and it's all liquid and you keep adding heat, the temperature is going to start going up again as it rises as a liquid. And then once again, once you get to the boiling point, it's going to stop its temperature change. And as it's vaporizing, the temperature is going to stay constant once again. And then once it's all boiled away and has turned into a gas, if you keep adding heat, that temperature is going to rise some more. So this is what we call a heating curve. And we need to know that this bottom region down here is a solid, the one here in the middle is a liquid, and of course the one up here is a gas, and we have melting and boiling. Very often on the AP exam, they'll have this diagram, except of course they won't label the solid, liquid, gas. They won't label the melting or the boiling. You have to know that part of it. Now, sometimes they actually draw this curve in reverse, where it starts off at a high temperature and then it drops. That's called a cooling curve, essentially because you're going in reverse. Now, let's take a look at another example of thermochemistry here, and this is where we can calculate the value of delta H. And whenever we have a question like this, we have to use the equation delta H is equal to the sum of all the enthalpies of formation of the products minus the sum of all the enthalpies of formation of the reactants. It's right side minus left side. And in this question, it says that the delta H of the reaction is equal to 149.7 kilojoules per mole. Determine the heat of formation of sodium hydroxide. Now, in this case, they don't tell us what the enthalpy of formation of sodium hydroxide is, but they are going to tell us the values for the sodium oxide, Na2O, and for water, H2O. So if we don't know sodium hydroxide, we can call that X, and since there are 2 moles of that, we have to multiply that value by 2. So X times 2, of course, is just 2X. Now, perhaps they tell us that the value of sodium oxide is negative 416 kilojoules per mole. There's only 1 mole of that, so it's still negative 416. And then they might tell us that the heat of formation, or enthalpy of formation, same thing basically, of water liquid is negative 285.8 kilojoules per mole. 1 mole of that, so it's still the same. And so when you add up the reactants, well, we just have 2x. Whenever you add up the products, we can punch this into a calculator and see that it's about negative 701.8 kilojoules. Now, once again, the equation is delta H equals the sum of the products minus the sum of the reactants. The delta H is given to us in the problem up here as 149.7. The sum of the products is negative 701.8. And the reactants would be 2x. And so now we just have an algebra equation that we have to solve. If I add 701.8 to both sides, I get negative 2x equals 851.5. If I divide both sides by negative 2x, I find that the enthalpy of formation of the unknown, the sodium hydroxide, is somewhere very close to negative 426 kilojoules per mole. So we can calculate the enthalpy of formation of a missing value. Sometimes they might give you the enthalpies of formation of all the reactants and products, and all you have to do is solve for the overall delta H. And that's probably the way that most students learn how to do these problems. Now, let's move right on to equilibrium, which is Unit 7. And the most fundamental idea here about equilibrium is being able to write an equilibrium constant expression. At some point, you're going to have to do this on the exam. And remember, it's products over reactants raised to the power of the coefficients. You only put in gases and aqueous solutions. Liquids and solids are omitted from equilibrium constant expression. So if we have this equation right here as an example, and we're asked to write the expression for Kc. Kc is in terms of concentration. That's what that C stands for. So we're going to use the brackets in that case. So it's going to be the concentration of Al3 plus all over the concentration of Ag plus cubed is equal to Kc. So there's your equilibrium constant expression. Whenever you're writing these, don't forget the Kc equals part of it. An expression is just that. It is an equation. If you don't write it as an equation, you're not going to get the point. Once again, leave out the solids. Notice that the silver solid and the aluminum solid are not a part of this. Now, what if we have this expression here, this equation, and we're asked to write the Kp. Now, P is in terms of pressure, so we don't use brackets in this case. We use the parentheses in the partial pressure notation. So in this case, Kp is equal to the partial pressure of NO, quantity squared, because there's a 2 right there, times the partial pressure of N2 all over the partial pressure of N2O, quantity squared. And we're using gases here, so everything gets included in that equilibrium constant expression. Now let's say we have an equilibrium problem. In this case, it says at a certain temperature, the reaction below occurs, and the chemist investigates the process by filling a container with N2O gas to a pressure of 1.00 atmospheres. After the mixture attains equilibrium, the pressure of N2O gas has dropped to 0.80 atmospheres. Calculate the equilibrium constant Kp at this temperature. So whenever we have initial values and final values, I would strongly recommend using an icebox for this type of problem. Now it says that the initial pressure of N2O is 1.00 atmospheres. So that's going to go in right here for the initial pressure of N2O. There's nothing else in the container at the initial state, so we can put in zeros for those other two initial values. The problem tells us that at equilibrium, N2O has dropped to 0.80 atmospheres. So I'm going to put 0.80 atmospheres in right there. Now in my change row, I have negative 0.20. That's the change from 1 to 0.8. Now on the other side of the arrow, we know that NO and N2 are going to have to increase. If the reactants went down, the products have to go up. And the NO is going to go up by 0.20 because it is a 2 to 2 mole ratio. So however much N2O goes down by is the same that NO is going to go up by. Now N2, it's a 2 to 1 ratio. So that means that the N2 only goes up by half as much as the NO went up by. So if NO is a plus 0.20, N2 is going to have to be plus 0.10. So that tells us that our equilibrium pressures are going to be 0.20 for NO and 0.10 for N2. Now, that's all very good, but that's not what the question is asking for. It says calculate the equilibrium constant Kp at this temperature. So what I'm going to have to do is write the equilibrium constant expression, products over reactants, raise the power of the coefficients, just like we did earlier, and then plug in those equilibrium values into the expression, and we can use our calculator and find that the answer is 6.3 times 10 to the negative third. And so that's the value of Kp. Now notice that this is a fairly small number. When I say small, I mean less than about 0.1. And generally speaking, the smaller the value of an equilibrium constant, the less amount of product you're going to have. And that's basically what we have here. We have a moderately small equilibrium constant. So that means we have a whole lot more reactants than we have products. We have 0.80 atmospheres of the reactant and much less product than that. And so that's the significance of the small equilibrium constant. Likewise, if we had had a very large equilibrium constant, larger than say about 10 or something like that, then we would have more product and less reactant. That's usually how that works. Now let's move on here and take a look at another equilibrium problem. This time it says at the same temperature as the previous example, a mixture of 3 gases was added to a closed container. The partial pressure of N2O gas was 0.72 atmospheres. The partial pressure of NO gas was 0.12 atmospheres, and the partial pressure of N2 gas was 0.16 atmospheres. We have the same equation. Part A says, what is the total pressure in the container? Well, once again, the total pressure is just the sum of all the individual partial pressures. We just add those 3 together, 0.72 plus 0.12 plus 0.16 atmospheres, and the answer is about 1.00 atmosphere. That's our total pressure. Now part B says, as the reaction proceeds, which gases will increase in pressure and which gases will decrease in pressure? And so on this problem, we have to use the reaction quotient. Now the reaction quotient is products over reactants raised to the power of the coefficients, but we call it Q because it's not necessarily at equilibrium. So we plug these pressures in here. The NO is 0.12, that's got to be squared. The N2 is 0.16, and the N2O is 0.72, and that's got to be squared. And when you calculate the value for Q on your calculator, you find that it's equal to about 4.4 times 10 to the negative third. Now we have to compare Q with K. And it looks like Q is less than K, because on our last problem, we just calculated that K was 6.3 times 10 to the negative third. So Q is less than K. Now, if you have trouble remembering what that means, I would strongly recommend drawing in the Pac-Man, just like this, just like we saw in the daily videos and in the unit summary video there on the Ultimate Review Packet. So it looks like the Pac-Man is eating toward the right. And so it's eating toward the product side. And so since it's going toward the product side, that means that the products NO and N2 are going to increase in concentration, or in pressure in this case, and the N2O, the reactant, is going to decrease in pressure. Now let's take a look at another equilibrium question. This time we have Le Chatelier's principle, and it says, after the reaction has returned to equilibrium, how would each of the following changes affect the partial pressure of N2 gas in the reaction vessel? So let's say we have some NO gas removed. Well, anytime we remove an object from equilibrium, the reaction is going to adjust itself to replenish whatever we just removed. So in this case, if we remove the NO, then N2O is going to react in order to increase the value of NO. And that's going to increase the N2 as well. So N2 pressure will increase in this case. How about if we add some N2O? Well, once again, when you add something to a system at equilibrium, the system is going to adjust itself to deplete whatever you just added. So if we add some N2O, the reaction is going to use up some of that N2O, and we're going to make more NO and more N2. So the partial pressure of N2 will also increase in that case. What if we add some argon gas? Well, once again, argon gas has nothing to do with this reaction. It is basically an inert gas in this reaction. So the answer is nothing is going to happen. There's not going to be any change when we add some inert gas like argon or neon or helium, something like that. What if we increase the pressure by decreasing the volume? Well, when you decrease the volume, increase the pressure, the reaction adjusts itself to move toward the side that takes up less space, which is the side that has fewer moles of gas. So in this case, that is the reactant side. It has 2 moles of gas versus 2 plus 1, 3 moles of gas. So that means that the reaction is going to shift toward the N2O. So that means that we're going to increase N2O, and NO and N2 are both going to decrease. And so that's why we say the partial pressure of nitrogen will decrease in this example, or in this part anyway. How about part E? The temperature of the container is increased. This is the one that trips up some students. We have to think about this in terms of delta H. The question says that delta H is a positive value. That means it's endothermic. Remember that endothermic processes imply that heat is a reactant. Heat is being absorbed. And so that's why I write heat as a reactant here. If we increase the temperature, that's the same thing as adding heat. So if you add heat, then it's going to shift toward the product side, isn't it? So we're going to increase the amount of NO. We're also going to increase the amount of N2. So that will increase, while the N2O, of course, would decrease. And so that's how you answer these questions involving Le Chatelier's principle. Now, let's move right on to Unit 8, which is acids and bases. Let's take a look briefly at the relationships between the hydronium ion concentration, the hydroxide ion concentration, pH, and pOH. Now, we need to know that H3O plus, the hydronium ion concentration, times the hydroxide ion concentration equals Kw. And as long as we're at 25 degrees Celsius, that value for Kw is about 1 times 10 to the negative 14th. So those are some very important values to use. Now, they'll give you these equations on the equation packet, but really it's in your best interest to know these ahead of time as well. This is telling us that at 25 degrees Celsius, the concentration of hydronium ions times the concentration of hydroxide ions equals 1 times 10 to the negative 14th. And we have another pair of important equations here. pH is equal to the negative log of the hydronium ion concentration, and pOH is equal to the negative log of the hydroxide ion concentration. So with this set of equations here, we can answer all kinds of things about pH, pOH, hydroxide concentration, hydronium concentration. Let's say that at 25 degrees Celsius, a solution has a pH of 4.12. Determine its pOH, its hydronium ion concentration, and its hydroxide ion concentration. Well, the pOH part is probably the easiest. We know that pH plus pOH equals 14. So to solve for pOH, we just have to take 14 minus that pH. So 14 minus 4.12 is about 9.88. So that's the first part of this. Now, the hydronium ion concentration, we're going to use this equation right here. And so to find the hydronium ion concentration from the pH, we have to take the negative antilog, which means we have to take 10 to the negative pH power in order to find hydronium. So if the pH is 4.12, we have to take 10 to the negative 4.12 power on our calculator. And so that's equal to about 7.6 times 10 to the negative 5th moles per liter. Now, the hydroxide ion concentration is done pretty much the same way. It's 10 to the negative pOH power. So we just calculated earlier that the pOH was 9.88. So the hydroxide ion concentration is just 10 to the negative 9.88 power. So that's about 1.3 times 10 to the negative 10th. Now, if you take the hydronium ion concentration and the hydroxide ion concentration and multiply them together, you'll find that the answer is pretty close to 1 times 10 to the negative 14th. Not exactly because of rounding, but it is pretty close. Now, speaking of acids and bases, it's important that you're able to work with strong acids and strong bases. You have to recognize the strong acids. The AP curriculum sets out 6 strong acids that you have to know. Now, some textbooks and some teachers may include some others. That's great. These are the 6 that you have to know. Hydrochloric acid, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. And the concentration of an acid, if it's a strong acid, is equal to the concentration of the hydronium ions. And so, for example, if we want to find the pH of a strong acid, all we have to do is take the negative log of that strong acid's concentration. So for example, if you have a question where it's 0.15 molar nitric acid, you have to remember that nitric acid is a strong acid. So to find the pH, you just take the negative log of 0.15, and you find that the answer is 0.82. Now, how about the strong bases? Well, the strong bases are the group 1 and 2 hydroxides. Now, some of these are not very soluble, so we don't work with them very often, but these are the most common strong bases that you would probably see on the AP exam. Remember that for any strong base, the concentration of the hydroxide ion is equal to the concentration of that compound. Now don't forget that if you have the group 2 hydroxides, you have to multiply it by 2 because there are 2 hydroxides for every 1 formula unit in the compound. So for example, if you have 0.012 molar calcium hydroxide, and the question asks you to find the pH of that, well, you have to remember that the hydroxide concentration is 2 times that value. So the hydroxide is 0.024. So when you find the pOH, you take the negative log of 0.024, not 0.012. And when you do that, you find that the pOH is 1.62. And to find the pH, you take 14 minus that value. So you find that the pH is about 12.38 in that case. Now, let's take a look at what happens in the case of weak acids. So for weak acids and bases, remember, these are compounds that do not dissociate completely in water. And so you have to work them as an equilibrium problem. Basically, an icebox is my preferred method, my recommended method of solving these. So let's say we have a question where we're asked to determine the pH of 0.40 molar hypobromous acid, HBRO, and it tells us the Ka, the equilibrium constant here, 2.3 times 10 to the negative 9th. Well, it would be helpful to write the equation. So we have the HBRO plus water, and we know that the products are going to be the conjugate acid of the base. The base is water in this case, so the conjugate acid is hydronium, and the other product is the conjugate base of the acid. The acid is HBRO, so the conjugate base would have to be BRO negative. Now, as you write the icebox here, we start with the 0.40 molar as the initial concentration of HBRO. Of course, the products are 0, and we don't know any of the other values. So the change is minus X, and on the product side, it's plus X. So our equilibrium values are 0.40 minus X, X, and X. And now we have to write the equilibrium constant expression. So that's Ka equals hydronium concentration times the BRO negative concentration all over the concentration of HBRO. Now we can plug and chug. The Ka is given to us in the problem as 2.3 times 10 to the negative 9th. We have X and X all over 0.40 minus X. There's this little math trick that I recommend that you do so that you can avoid the quadratic equation and some extra steps. And you just ignore that minus X, and we can cross multiply, and we find that X squared equals 9.2 times 10 to the negative 10th. And now we take the square root, and you find that X is equal to about 3.0 times 10 to the negative 5th moles per liter. Now X in the icebox is shown to be the concentration of hydronium ions. So to find the pH, we take the negative log of the hydronium ion. So negative log of 3.0 times 10 to the negative 5th. So the pH is equal to about 4.52 once you plug that into your calculator. Now, sometimes they're going to ask you to calculate the percent dissociation. The percent dissociation for any weak acid is just the value of X that you got here divided by the initial concentration of the acid, times 100, of course. So in this case, it would be that 3.0 times 10 to the negative 5th, that was our X value, divided by 0.40, and then times 100 to get the percent as about 0.0075%. That's a very minuscule percentage of these HBRO molecules that dissociated. But that makes sense because notice the Ka value is very, very small. That's an exceedingly small Ka value. The smaller the value for Ka, generally speaking, the smaller or the lower your percent dissociation is going to be. And likewise, the larger the Ka value, the higher your percent dissociation is normally going to be. And of course, we can work weak bases in a similar way, except of course we have Kb, and we solve for the hydroxide value, and we find the POH, and then get the pH from that. Now, sometimes we have questions involving salts, ionic compounds, and this is something that I've kind of taken for granted in my daily videos, and sometimes we have questions about this. I'll have NaF, and I assume that students know that we ignore the Na because it's a spectator ion and we solve it as a weak base problem. But this is a good question. How do I know that NaF is basic and not acidic? Now, every now and then on the AP exam, they'll ask you questions about this. They'll give you an ionic compound, perhaps a random ionic compound, and they'll ask you, is this ionic compound or is this salt acidic or basic in its nature? And there's a little trick that we can do to figure that out. It's actually quite simple. All you have to do is take that ionic compound and add it to water. Now, as you write water, I would recommend that you write it as HOH. And what you do there is you just swap the ions just like you were writing a double replacement reaction back in first year chemistry. So the Na gets with the OH to make NaOH, and the H gets with F to make HF. And you realize NaOH is a strong base and HF is a weak acid. And so strong base versus weak acid, the base wins. And so that means that NaF is a basic compound. That's a little trick that we can use to kind of figure that out. Now, I'm not saying that NaF actually reacts with water like this. This is just a little trick to help us figure that out. Now, likewise, if we have ZnBr2, zinc bromide, we could do the same thing. We could add it to water and just use this little trick here to see if ZnBr2 is going to be acidic or basic. Well, in this case, the zinc gets with hydroxide to make zinc hydroxide, and then H gets with the Br to make HBr. Now, we know that zinc hydroxide is not a strong base, so it has to be a weak base, and HBr is one of our big six strong acids. So this time, it's weak base strong acid, the acid wins. And so that means that zinc bromide is somewhat acidic in nature. And what if we have something like this, like KCl, potassium chloride? Well, same trick. You can add it to water. And K gets with OH to make KOH. H gets with Cl to make HCl. And we know that KOH is a strong base. HCl is a strong acid. And guess what? Strong base, strong acid, they neutralize. That's a tie, which means that KCl is neutral. It's neither acidic nor basic. And so that's just a little trick that you can use to figure out if a salt is acidic or basic. Now, speaking of acids and bases, it's important to realize that in an acid-base titration, the goal of that titration is normally to determine the concentration of an acid or base. And very often on the AP Chemistry exam, you'll be presented with an acid-base titration curve. And it often looks something like this. Now, let's say that we have a question like this. If 10 milliliters of a weak acid was used in this titration, determine the acid's concentration. I would recommend that you use the titration equation for something like this. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And so the molarity of the acid in this problem is what we're trying to solve for. It says determine the acid's concentration. So we're solving for M sub A. Now, V sub A, the volume of the acid, is given to us in the question. It says it's 10.00 milliliters, so that gets plugged in for V sub A. Now, M sub B is the molarity of the base. Well, the problem doesn't say, but the titration curve does. It says it was 0.100 molar of base. So I'm going to plug that in there for the molarity of the base. And the volume of the base is a little piece of information that we have to get out of the titration curve itself. We see that the inflection point, this equivalence point right here, it's where it's labeled X, is at 25 milliliters. So that means that we use 25 milliliters of the base to get to the equivalence point. So now we just have to solve using simple algebra, and you find that the value for M sub A is about 0.25 molar of acid. So that's how you can solve a simple question like this using a titration curve. Now, how about if we're asked to estimate the Ka, the acid dissociation constant, of the weak acid used in this titration? Well, a key little nugget of information that you need to know is that at the half equivalence point, or halfway to the equivalence point, the pH at that moment is equal to the pKa, or the negative log of the Ka of the acid. So 25 milliliters got us to the equivalence point. So halfway there is 12.5. So it looks like it's right here. It's denoted by point V on this curve. That seems to be, it's kind of hard to eyeball that, probably somewhere around 5.5, 5.4 is the pKa of that acid. So that means that the Ka is 10 to the negative 5.4 power, which is around 4.0 times 10 to the negative 6. So we can estimate the Ka of an acid, of a weak acid, used in a titration just by looking at the titration curve. Now let's hone in on this titration curve a little bit more, and let's estimate the primary reaction component, of course other than water, present in the titration flask at each of the points labeled on the titration curve. Now at point V, notice that's the halfway point. At the halfway point, we are essentially at a point where the concentration of the acid is exactly equal to the concentration of the conjugate base. And so we can say that the acid and the conjugate base, HA and A minus, are equal at that point on the titration curve. Now how about point W? Well, notice that we have a pH that's higher, that's more basic than the halfway point. So it goes to reason that if we have a pH that's more basic than the halfway point, well, guess what's going to predominate? The conjugate base at this point. So that means that as the pH is rising above that halfway point, the conjugate base is the primary component. Now there is still some HA, some acid still there, but it is decreasing as that titration continues. At point X, we are at the equivalence point. All of the HA has been reacted. All that's left is the conjugate base. And so A minus, the conjugate base, is your primary component in the titration at the equivalence point, and essentially only at the equivalence point. Now, if we go past that point, we've overshot the titration. Well, if you just keep adding hydroxide, just keep adding, well, guess what's there? It's mainly hydroxide. So it's hydroxide, OH minus, that is the primary component in the reaction at those points, both Y and Z, because you've basically overshot the titration. Now let's move on to Unit 9, which is about the second law of thermodynamics and electrochemistry. So a very important concept in Unit 9, especially about the second law of thermodynamics, is this concept of entropy. Entropy is a measure of the total number of possible energy states in a material. Sometimes we talk about it in terms of how much disorder there is or how much chaos there is. Very often it's also described as a measure of how well dispersed a material is. So all of these are nice descriptions to help us understand and conceptualize entropy, especially in AP Chemistry. Essentially, we need to know that solids have very little entropy. They have the least entropy of all of your states of matter. Essentially, there's not much dispersal of the matter in a solid. In a liquid, the matter is somewhat more dispersed, and so we have more entropy. In an aqueous solution, most of the time, we have even more entropy than we had before. And then in a gas, of course, there's a whole lot of dispersal. Those molecules are moving around all over the place. So a gas has the most entropy of your states of matter. Now, it's important to realize that if you have a material at a higher temperature, that has more entropy than materials at lower temperatures. But what if you have perhaps two systems and they're both gases, perhaps they're at the same temperature? Well, the tiebreaker in that case is to start counting molecules, because a system with more molecules is going to have more entropy than a system with fewer molecules. So let's take a few examples here. Let's predict the sign of delta S, change in entropy for each of these processes. So in this first equation here, we have a solid that is transitioning into a mixture of a solid and a gas. Now, solids have the lowest entropy. Well, solid and gas would have higher. And so in this case, we're increasing entropy, so it's a positive sign for delta S. In this next equation here, it looks like we have a mixture of a solid and a gas transitioning into all solids. Once again, a solid and a gas changing to all solid, well, that's a decrease in entropy, so our delta S should be negative for this one here. Now, how about this case? Here we have two ions, those are aqueous, and they're transitioning to a solid. Well, aqueous has a moderately high entropy, solid has the lowest. So in this case, we are decreasing in entropy, so we have a negative sign for delta S. And then let's do one more here. We have this combustion reaction. Now notice that everything is a gas, and so states of matter will not help us here. Like I said earlier, if there's a tie, we've got to count the molecules. So on the reactant side, we have 5 molecules of gas. On the product side, we have 6 molecules of gas. So 5 to 6 is an increase in the number of molecules, hence that's an increase in entropy. So we have a positive sign for delta S in this case. Now, as we talk about entropy, it's also important to realize there's this concept of thermodynamic favorability. And this answers the question, is a reaction going to take place? And if it does, then we say it's thermodynamically favorable. Now, there are 2 driving forces that can determine if a reaction is going to be thermodynamically favored. The first one, which we learned about back in Unit 6, is enthalpy. That's the delta H. You might know that most of the reactions that you're familiar with in the lab tend to be exothermic because exothermic reactions tend to be favored by the universe. The universe likes exothermic processes. And so if you have a reaction that's exothermic, that exothermicity is a driving force for that reaction. Now, the other driving force is entropy. And we know that the universe likes it when entropy increases. And so if you have a reaction that has a delta S that's positive, then that's going to be a driving force. The entropy is going to be a driving force for that reaction. Now, if you ever encounter a reaction that is both exothermic and has increasing entropy, so that's a negative delta H and a positive delta S, then the reaction is really going to be favored, basically at all temperatures. If it's the opposite, though, if you have an endothermic reaction and it decreases in entropy, well, the universe doesn't like either of those. So that process is never going to be favored, no matter what the temperature is. Now, if only one of those driving forces is favored by the universe, the process is going to be thermodynamically favored only at certain temperatures. So for example, if the delta H is positive, endothermic, and delta S is positive, increasing entropy, that process is going to be favored only at relatively high temperatures. Now, likewise, if the delta H is negative, it's exothermic, and delta S is negative, decreasing entropy, then that reaction is going to be favored only at relatively low temperatures. And so we have to understand how that works. Now, how can we measure thermodynamic favorability? Well, there is a numerical value for that. We call that delta G. That's the Gibbs free energy. And there are a couple ways to calculate delta G, Gibbs free energy. We can use this equation right here. Delta G equals delta H minus T times delta S. We can also use this equation if we know the equilibrium constant. We can take delta G, and that's equal to negative R, which is 8.314 joules per mole per Kelvin, times the Kelvin temperature, times the natural log of the equilibrium constant. We can also calculate delta G in a similar way to we did earlier with delta H, the sum of the Gibbs free energies of the products minus the sum of the Gibbs free energy of the reactants. That's another way to do that. That could pop up on the exam as well. Remember that if delta G is a positive value, the reaction is not thermodynamically favored. On the other hand, if delta G is a negative value, then that reaction is going to be thermodynamically favored. So be aware of how that works for thermodynamic favorability and delta G. Now, the last few parts of Unit 9 have to do with electrochemistry. So let's take a look at a galvanic cell problem here. A galvanic cell, sometimes called a voltaic cell, is basically a battery. It is a thermodynamically favored process where we have essentially an oxidation-reduction reaction, or a redox reaction, taking place. Now, this is different from an electrolytic cell. An electrolytic cell is electrolysis. You have to put energy into that electrolytic cell. It is a non-thermodynamically favored process. It requires an external power source to run that electrolytic cell. In this example, though, we're going to look at a galvanic cell. This is the one that basically runs on its own. It's a battery. So here we have a picture, and I have silver and silver ions on one side of this, and on the other side I have nickel with nickel ions. Of course, I have some spectator ions. I have some nitrates and some chlorides thrown in there for good measure. And we want to take a look at the half reactions. Now, each half reaction is normally going to be given to you on the test. And so in this case, we have these half reactions. Notice that these half reactions are always written as reductions. That's just how we do it. Okay, I know that we have to have one reduction, one oxidation, but in the tables, they're always going to write them as reductions. And so in these, let's first of all calculate the total voltage, or the cell potential here. Now, the cell potential, the E cell, is going to be the standard reduction potential of the cathode minus the standard reduction potential of the anode. And the way we do this is we have to subtract these numbers in such a way that we get a positive value for E cell. Since all galvanic cells are thermodynamically favored, the value of the voltage, the value of the E cell, has to be positive. So that means that the more positive value goes in the position of the cathode, and the more negative number goes in the value of the anode. So we have to subtract it like this: 0.80 volts minus a negative 0.25 volts. And so our E cell is 1.05 volts. If we had tried to subtract it in the other direction, we would have gotten the negative value, and you can't have a negative voltage for a galvanic cell. Now, this also tells us some information. It tells us that the 0.80 volts, that's the value for silver, is the cathode. So that means that silver is the cathode. And we know that reduction always takes place at the cathode. And the negative 0.25 volts, that was the value for nickel, that is associated with the anode. So the nickel is the anode, and oxidation always takes place at the anode. Couple different ways to remember that. Anode and oxidation both start with vowels. Cathode and reduction both start with consonants. Or if you prefer, red cat and an ox. That's how I tell my students to remember that sometimes. Now, we know that in the galvanic cell, the electrons are going to travel through the wire from the anode to the cathode. So like this. Think about AC, as in like air conditioning, anode to cathode, AC. So it always travels in that direction. Now, let's take this one step further. Let's write the overall balanced equation. Now, we know that the cathode half reaction is written as it is. So that means that the silver half reaction stays just like it was in the chart here. Well, the anode is the one that you have to flip around, whereas I say flip an ode. Okay, so the anode gets flipped around, so it's Ni yields Ni2 plus 2 electrons. And whenever you add the two half reactions, you have to make it so that these electrons cancel out completely. So they're not canceling out completely right now, so I have to multiply the silver equation by 2, just like this, so that the 2 electrons will now cancel out on both sides. And so the overall balanced equation is 2Ag plus Ni yields 2Ag plus Ni2 plus. Whenever you have a galvanic cell with metallic electrodes like this, I always tell my students the cat gets fat, which means that the cathode increases in mass. So the cathode is the silver, so as the reaction runs, you're going to see the mass of silver over here increasing, and then the anode is going to decrease in mass. So this Ni, this nickel, would be being corroded away and would actually decrease in mass. At the salt bridge, don't forget that cations flow toward the cathode and anions flow toward the anode. So if you were to zoom in on this, if there were any cations like sodium or something like that, it would be flowing toward the cathode in this direction. The anions, like maybe chloride or most likely nitrate or something like that, that would be flowing toward the anode over here. Wow, that was quite a ride. I hope that was helpful to you. And if it was, please remember to like this video and don't forget to share it with your classmates. I hope you do a great job on the AP exam. Just remember what you've learned all year. You've spent this whole year working hard on this course. Now it's time to shine. So go out there and get that score. Thanks for watching, and I'll see you soon.